Go be sick somewhere else.
Now I know y'all are in physics, and I know sometimes the calculus class helped you out in physics, and I know sometimes the calculus class is behind this. So some of y'all may know what centromass is, some of you may not. But we'll go ahead and talk about it. We're going to start good today, aren't we? Centromass. Moments. We'll start with moments. Moments and center of mass. In my opinion, moments help us get the center of mass. The principle that you learn with moments help you with center of mass. The difference between moments is more two-dimensional. Well, no. Moments is more when you have a balance versus when you have an irregular shape. Alright? Moments is best explained like on a seesaw or a teeter-totter or a balance or a lever system, where center of mass is usually like on a blob of metal or a blob of ceramic or a blob that's irregular shape. So, are they kind of the same thing? Yes, but this one is pretty much based off of this. What is a moment? Fulcrum, lever, you got force on this side, you got a force on this side, F of 1 and F of 2, and D1 and D sub 2. Now, in the perfect world, those forces are the same, correct? In Mayberry, they are the same. But we all know that we can't base everything on the perfect world because it's not perfect. So we have to think about what if this force is more than this force. Well, common sense would dictate if you have put a heavier force, let's say 100 pounds here and 50 pounds here, then the fulcrum, to balance, would have to move which way? To the left. But how much? So that's why we study moments, to figure out where the fulcrum needs to go to balance 150 pounds of force. And that's what moments are. Center of mass is when you have an irregular object. I like to explain center of mass. Let me move this over for a minute, because I do like to explain stuff before I show you how to do it, because there's nothing that infuriates me more than somebody that goes through a whole unit and don't know what they learned. Alright? That's moment. Center of mass, I like to explain. Some of y'all may remember people that takes plates and balances them on the dial like that. Y'all seen people do that? Like clowns and stuff, they'll take the plates and they'll spin them and they'll do all kinds of things. Alright? Center of mass here is just like Mayberry. Okay? Why? Because you know that the weight of the plate is evenly what? Distributed. So there's no problem. But what if you have a piece of metal like that? Well, you know that it weighs more here than it does here, because what? There ain't nothing there. Alright? There's air. So if the center of mass was here, where is it going to be now? Well, it's going to be down this way because of the weight distribution. All right? So you have to, so this is a perfect world. This is Mayberry. That's why everybody loves Mayberry, because it's a perfect world. This is a perfect world. Alright? We're not going to study those. We're going to base the principles off of the center of mass and off of those. But the imperfect world with this would be Susie. There's no women in here, so Susie weighs 200 pounds. And Jody weighs 75 pounds. Well, there ain't nobody else on the dadgum playground, so they're going to have to move the fulcrum over toward Susan because you fork her. Okay? I mean, for second grade, 200 pounds is pretty big. She's an outlier. Alright, so this is the real world, and this is the real world. So, what do you do to find the center of mass? Well, for the moment, let's take an example. Let's say we've got fulcrum and lever, and this is a test question because I'm gonna give you moment, but I'm gonna give you center of mass questions. And let's say you got 5 kilograms, 50 newtons, 5 kilograms, and G is equal to 10 meters per second cubed. And that's 50 newtons. And then over here you got 10 kilograms, which is 100 newtons. And they want to know where the fulcrum needs to be placed. Well, we know we can take 50 times 10 is equal to 100 times D. Because we've got distance here. We'll call that DC1. We've got the distance here, which is DC2. And we're just trying to find D right now. Huh? The 10? No. We're basing that off of the 10 meters. I mean, yes, we're basing it off of 10 meters, whoever asked that. So that comes out to be, now this ain't the actual question I'll give you, I'm just showing you this. You just hold tight, and we'll get to the question and you'll understand it a whole lot more. 500 is equal to 100D, and D is equal to 5. Okay? Now, if we wanted to find D1 and D2, I'll show you the best example here in just a second, find a moment, and that's with multiple forces right here. So let me show you that one, and then you'll start seeing how to actually find it. So let me go show you this one. You got a fulcrum, and I mean a lever and a fulcrum, and we've got a 10 Newton force going up at 8 meters. And let me draw a thing here. And a 5 Newton force that's at 6 meters. And a 50 Newton force at 2 meters. That's 2 meters right there. And then a 6 Newton force at 3 meters. And then this force at 10 meters, we need to know what force is there at 10 meters to balance it out. Now, when you're dealing with forces going up and down, I like to tell students clockwise and what? Counterclockwise. So, your 10 times 8, that's going which way? Going clockwise, right? So, on clockwise, that's going to be 10 times 8. Because what is work? Force times what? Distance. So 10 times 8 in the clockwise position. 10 times 8. Now which way is this one going? Counterclockwise. So draw you a little, let's see, counterclockwise. That's this is counterclockwise. So that would be 5 times 8, or 5 times 6. Okay, let me just do this. This might help you. Alright, next one is clockwise, and that would be 50 times what? 2. Finish it out. You got a variable in there, and that variable is what you're going to find for, or what you're going to solve for. All right, which way is these guys going? What? Counterclockwise. So that's going to be 6 times 3. going to be 10 times x. So now you can set up the equation, and of course the fulcrum is the equal sign. So that's going to be 10 times 8 plus 50 times 2 is equal to 5 times 6 plus 6 times 3 plus 10 times x. And then 80, what is it? 80 plus 100 is 180. Is equal to 30 plus 18 is 48. Somebody help me out. And then 180 minus 48 is what? 32, 132, huh? And x is equal to 13.2. So you've got a, and you might not want to call it x, so that'll get you mixed up with this, so call it y. And so you've got a force of 13.2 newtons going up. Remember, force is equal to work is equal to force times distance. All right, let's do a nerd. Haven't got into the calculus yet. This is all algebra. Got 10 newtons. And I'm just going to put negative 10 meters. In other words, this way, 10 meters. And then got 8 meters. I'm sorry, 8 newtons. No, shoot. I read my own back here, I'm writing. 50 meters, 50 newtons at 8 meters. And then 5 newtons at negative 4 meters. And 10 newtons at 3 meters. And 20 newtons at 8 meters. And how many newtons at 10 meters? So work on that for a second. No coffee. I need to drink more juice. People say I'm loud. you eating the whole bag. I don't know how that is. Get all your clockwise and get all your counterclockwise. Now, let's go with, well, we'll just go from left to right. And, what's wrong with this thing? Of course, it's not the operator. It's never the operator. Right? Limit on. It's all y'all's fault. Y'all brought me this one, not the odd. Alright, so you can do this. This is something I do. That's what? Clockwise. What is this one? So you do a circle there. Clockwise. What is this one? So it's circle. What is this one? It's clockwise, so and this one is so now just do put all your clockwise on one side. So that's 10 times 10 plus, so that takes care of that one, plus this one is clockwise, so that'd be 5 times 4 plus 20 times 8 is equal to 50 times 8 plus 10 times 3 plus 10 times, we'll call it F. And then that's going to be 120 plus 160 is 3. Help me out. What is it? 260, 280? 280? Yeah, 280. And then we've got 400, 430 plus 10F. And then minus 430, I got negative 150. Y'all check me. So F is equal to negative what? 15. And what does that negative mean? That means it's going which direction? It's going clockwise. So it'd be, let's see, that'd be going down. Or you could just say negative is going down. So you could say, just erase this. I'll put it in blue. And that is how many? 15. So there's 2 questions we just did that you can pretty much guarantee be on the test, even though there's not much calculus. That's the whole thing about the center of moment. And let's go to center of mass. Find one. I don't want to. Let me pull up the book right quick before I go into this. This is the right book, isn't it here? Application of integration. You're not going to the center of mass in this book. Is it the next chapter? Okay, well, I'm sorry. I thought, wow, I didn't know that. I'm sorry. I may not even have to go into it. Huh. Let me just keep going and see. I thought it was in this chapter. Because you use integration. Huh? I know. No. Somebody got a book. Dang old, look it up in the index. See where they got dang old center of mass. Dang old row. I can't read this thing. Contents don't help me. No, because that's... I'm sorry, what? 554? Wow. They just put it in another chapter. Oh well. Because there's what the center of mass is right there. Dang old plate, dang old milk. Moment and center of mass. Thank you. Now, rho is in here, but rho, I don't want you worrying about rho as much because rho cancels out. The only time you need to worry about rho is when you are in physics and you're talking about the material and the makeup and the density of the material. Everybody with me? Yeah. All right, so we're not going to worry about rho. Rho will cancel out. Let me pull this up now and see. Okay, here we go. Yeah, this is it. All right. Well, I'll make amends on the next unit, but we're going to go ahead and finish today's lesson because that's what I already planned for. I had no idea they included in another chapter. All right. That's what we just got through talking about right here. Okay, here's where we start talking about center of mass right here. There we go. This is what I wanted to pull up. I want you to write these two things down right here. Your X bar and your Y bar. Say again, what? No. You just need to get some dang glasses. Dang old blind.
Priority 1 message coming in on secured channel.
All right. Now, make sure you realize that for the X bar, the moment around the Y axis is used, and for Y bar, the moment around the X axis is used. And if you think about it, you're trying to find, like, here is your, I don't know, this is, I can't, they showed a good example of this in the other book, but you've got to take in the effect this distance right here from Y and the distance from what? X. And you have to think about it as the center of mass. If you're talking about X bar, then it's going to be spinning around the Y axis. So you got to think of it in terms of that, and I think that's what this is doing right here, this example right here. So take a look at this example, and we'll do one a little bit more difficult than this one. But it says, find the moment and center of mass of the system of objects that have masses 3, 4, and 8 at the points, blah, 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 blah. All right, so I'm going to draw this, and the reason I want to draw it on the board is I want to explain what we're actually finding. So take a minute, and I want you to draw a graph, and I want you to draw the 3 points. Basically, you've got a triangle. Just think of it as a piece of metal that's shaped like a triangle. Okay? So I'm going to freeze it right there so I can go set it up on the board. Can y'all see it? Is that good enough? Or, well, is that all 3 points?
Yeah.
Okay. All right, freeze. Let me go pull up the whiteboard and I'll draw it for you. Dang old, got to turn on the dang old grid. Visible, there we go. Close. Now, did I hear you correctly when you said this is your 4th year of calculus?
Yeah, I took both semesters of calculus in high school, but
Okay. Well, you did it the way you're supposed to. I just didn't pass the first couple of times. So I was just wondering if you were in my same boat as I was. I just wouldn't listen. I didn't want to know what the distributive law was, and I didn't need to know, so I tried to take calculus when I didn't even know how to do algebra. And you can't do that. Durr, as Medea would say. Hello. All right, our problem. Let's see, how can okay, can y'all give me the points? Since y'all are looking at it and I'm not. What's the first point? All right, I'll do it in red. -1 and what? Okay, -1, +1. And what's the other point? 2 and what? -1. And what's the other point? 3 and +2. +3 and +2. All right, let me draw a handy dandy drawing here. Better not use my chicken scratch. All right, so there's our handy dandy points right there. And just think of this as a plate, a metal plate. But instead of, I got a dashed line. I ain't got no dashed line on this thing. Let me do this on here. There it is. Dang old, could be a full rectangular plate. Now, if it was a full rectangular plate, where would the center mass be? Well, center mass would be midpoint, and midpoint would be right in here, wouldn't it? But is that the perfect world? No. So, if this is gone, if this is taken away, now what I'm trying to show you is a little bit of common sense. Maybe we need to invite our all right, now, when that goes away, what does it do to your center of mass? Does it send it in this area up here, or does it move it down? It moves it down. So, it's going to be down here somewhere. Okay? Little common sense. Now, what do? Well, you use your force is equal to, weight is equal to force times. Work is equal to force times distance. So let's go to it. Now, do you remember Kramer's rule? Back when in algebra you had to study Kramer's rule, and you had to find the determinant. and then you had to define the determinant of x, and then you had to find the determinant of y, and then you had to put the determinant on the bottom. You remember doing that? Y'all suck. Anyway, this is the same thing. Only your determinant is going to be your m, your moment. Your moment around the y-axis is going to be your numerator for x bar, and so on. So, first you got to find your moment. Well, what is the moment? Well, if you look, what is the moment? What? Where? How'd you get it? No, not the moment. I mean the moment right here, the m, right there. Where did they get m? Well, m is the summation of m sub I. Is the total what? Total mass. So m is your denominator, and it's just the total mass. Well, what's the total mass? 8 plus 4 plus 3 is... Okay, so you got your moment. So the first thing is we got to find our moment, and we just did that. Let me go back to my handy dandy. Okay, Hubert, where is it? There we go. So what's this one? 8. 8. Thank you. Let me fix this. Blow it up and fix it so you can see. Okay. No problem. Alright, this is 8. 8 what? Okay, and what is this? 4 and 3. So m is equal to the summation of the masses, which is equal to 8 plus 4 plus 3, which is equal to 15. And 15 is the denominator. Okay, now we got to find the moment around the x-axis and the moment around the y-axis. So what they're asking is, thinking about around the x-axis and around the y-axis. So that's going to be, that's where your points are going to come in. So that's going to be, what is this? -1, +1 at -1, +1. And this one is 3 and 2. And this one's at 2, -1. Now, they give you, in the example, they give you the formula to do that, which is based on force times distance. There it is. So, for y and x, if you look right there, 3, what's the number we multiply by 3? -1. Well, I thought, Hubert, I thought you said that's the y. Yeah, but you have to do the opposite, because right here, moment around the y-axis, 3 times -1. The mass of 3, but what? -1 is what? The x coordinate. And you have to remember that. Now, what's the most common mistake? The most common mistake is when people forget that. So, do the mass times the distance for m sub y, and do the mass times the distance for m sub x, and then that is your numerators. Just like Kramer's rule. So go ahead and do that. of y. I'm going to take my, and we'll read from left to right. Let's go from left to right. So here's my first one, 3 whatevers times what? -1 plus, let's see, this one comes next because we read from left to right. So this one's 4 times what? 2, Hubert. Thank you, class. Plus 8 times what? 8 times 3, Hubert. Now, why, somebody tell me why it's x? Because you're revolving around the what? So, think of it kind of like swinging a bucket. You know, swinging a bucket, dang old centrifugal force, dang old water stays in the bucket. Okay. You're swinging it around. Well, what's taken into effect? The x coordinate. And that's the best way to see that is on the dang old graph. Alright, so 3 times -1, -3 plus 8 is dang old 5. 5 plus 24 is what? 29. And that's your numerator. And then m sub x, we're revolving around here, so dang old that one. Yeah. So 3 times 1 plus 4 times what? -1. Make sure I don't mess up. And be 8 times 2. And it is very important, I'm telling you, to take the time to draw this stuff out, because I'm going to tell you, you're going to forget on the test, and you're going to get so pissed when you have done a problem wrong just because you put the wrong coordinates in the calculation. You're going to get mad, I'm telling you. And that comes out to be 3 minus 4 is -1. -1 plus 16 is 15. Okay, so the moment the center of mass is going to be equal to the moment around the y-axis over m times the moment around the x-axis over m. And what's the moment? Let's see, the moment around the y-axis is 29 over, what was our 15? And 15 over 15. So that's going to be what? A little less than 2 and 1. So let's go 2 and 1. 1, 2, and 1. So there is our center of mass. Well, actually, it's a little bit less than 2, isn't it? What is that, 1.9? Yeah, 1.9, a little bit over. 1.9 and 1. We got to get close to our estimate. So we always got to be right. So. Now, this is a very basic problem. But the reason you start with the basic is you got to crawl before you can what? One person knows to walk. Okay. Your parents fall. All right. Now, we got to get some integration in here soon, or y'all not getting your money's worth. So, I like that one. And here's where you get into the integration. I'm not going to go over that, but when you apply integration, you got to hold your pinky up because you can't call it center of mass anymore. When you apply integration, you got to hold your pinky up and call it the lamina. Okay? The lamina. So, the center of mass in the lamina, because it's a blob. Okay? It looks like an irregular object. All right? And they're going to go through the whole spiel there about the area under a curve. We don't need to do that because y'all know the area under a curve. And here is what you need to know. These two formulas right here. You don't need to know Ryman's over here. You just need to know this. And there's your rho. Dang old Winston Road. Dang old Star Trek. All right. Delta x is rho times the antiderivative from a to b of f(x) times f of x dx. So write that down. And then your delta x is equal to p, your moment around your y-axis. Yeah, the moment around the y-axis. I'm sorry. The moment around the y-axis. The moment around the x-axis is rho 1/2 f of x quantity squared. Now write those two down, and you're going to have to put them to memory because unless you're just going to put them on a card or something, that's fine too. I don't care. But that's going to be how you find your integration, your moment around your x-axis and the moment around the y-axis. So take a moment and write those down. Huh? F of x quantity squared. Oh yeah, y'all can't see it. I'm sorry. I know, I suck. I suck as a teacher. It's my fault. It's my fault that we're not on a 2-hour delay. Yeah. I don't want to take the blame. I'll blame it on Bush. Well, luckily, there's an easy part to it, and that is the m is going to be equal to something simple, the antiderivative of f of x dx. So, write that down. M is equal to the antiderivative of f of x. So again, rho is going to be in front, so what's going to happen to the rho's? They're going to cancel. The reason you don't get into rho's, R-O-E-S, is because we're not mixing the metals and we're not mixing the materials. Now, if you have a piece of metal that is made up of two different thank you, then you've got different densities, which makes a difference. If you've got a piece of metal or a blob or a lamina and it is half aluminum and half steel, then you got something totally messed up. All right, you can't find out where the middle is because of the two densities. So that's where rho comes in. All right, so write those down, and then the moment that goes in the denominator is rho times the antiderivative from a to b of f of x dx. And all you've got to remember is this part right here. What is the moment around the x-axis? It's the moment around the y over the moment. What is the moment around the y-axis? It's the moment around the x over the m. If you remember this, and you have those two integrations written down, then all you got to do is plug and chug. But if you don't remember that if you don't remember that basic thing right there, if you don't remember this, then all that other stuff ain't worth crap, because you're gonna put this over this for the X, and you're gonna put this over this for the Y, and you're gonna have everything bass what? Bass backwards. Some of y'all might need to look that up. Because of your parents. All right. All right, let's take something simple. I've got this one in my book. In my notebook right here. Find the center of mass of a semicircular plate of radius r, and that's all they give you. All right, so find that, and they give you the function f of x is equal to that. So take that and see what you can do with it. And I will try to find you another example. Can y'all see it? Hold on.
Yeah.
I'll make sure it's. I don't want some of y'all to be deprived of the picture. What? It's only a sentence. Find the center of mass. You're going to have to stop that coughing. You're going to have to get well, okay? Okay, there's the one I got. Find the centroid of the region. Yeah. Yeah, that's one. This one, the one I've got here, is one where you have a line going across it. So this one's easy, and the next one's going to be a little bit more difficult. All right, common sense time. I want to ask y'all a question. If you have something that's symmetrical, and you're wanting to find the center of the mass, or center mass, if something is symmetrical, then basically it's the same on both sides, right? So if it's the same on both sides, then one direction, you're not going to have to figure the center of mass. You can just plot it algebraically. And in this case, where's my... In this case, the symmetrics is around what? The x-axis, the y-axis. Here's the symmetry. Line of symmetry is right here. Now, if the line of symmetry is right there, then you know that your center mass is going to fall on this line as far as x goes. Okay? So, your x is going to be for your center mass of the triangle, or not the triangle, the whatever this is called, semicircle. Alright? Your x is going to be 0. So you don't even have to figure that. Or I'll figure it for you, 0. You're welcome. So now we got to figure the y. We got to figure this. So that's going to be 1 over pi r squared from negative r to r. Negative r to r of 1/2 dang old this squared. So plug and chug. Y bar is equal to 1 over pi r squared. Help me out. Make sure I didn't. Is that pi r squared? The area of the circle of pi r squared? Or would it be 1/2? Be 1/2. Wouldn't it? You can put the 1/2 in there, or you can divide it by 2. It doesn't matter. From negative r to r of 1/2, and plug in the square root. Where is it? Square root of r squared minus x squared to the second power and dx. And that's probably what they did on the next page. Yep, they did divide it. I figured they did. Or you could divide it by 2. Whichever one you want to. That would be 1/2. So now clean this up. Because that's all you need to do is clean it up, because you're going to rewrite this as r squared minus x squared to what power? To the 1/2 power. And then what's 1/2 raised to the second power? 1. So that takes care of that. The 1/2 comes out, and it'll cancel out some of that stuff. So you basically got a easier problem than you think, especially when you clean it up. So that's going to give us, let's pull this 1/2 out. Let's pull it out here. So y bar is equal to let's see, 1/2 over 1/2 pi r squared, and the 1/2s do what? They cancel. So that leaves us with 1 over pi r squared times the antiderivative from negative r to r of r squared minus x squared to the 1/2 power raised to the second power dx. And that's going to give us y bar is equal to 1 over pi r squared of negative r to r of r squared minus x squared dx. And they're basically going to use implicit differentiation. Let's see. But that's going to be, you can break it up into 2 if you want to. So I'm going to break it up. Y bar is equal to 1 over pi r squared, antiderivative bracket, antiderivative from negative r to r of r squared dx minus antiderivative from negative r to r of x squared dx. And what do we do here? it's not rhetorical, I'm asking y'all. What's the antiderivative of x to the 0 power? X to the first over 1, right? So that's going to come out to be r squared x right here, right? But what? Look, we're leaving something out. What's the problem? What's the problem there? Huh? dx. There's an r there. What do we got to do? You still got to take. Remember doing implicit differentiation? I know this is not differentiation, but what do you have to do since it's integration? I'm not asking, I mean, that's not rhetorical, I'm asking y'all. I said it's based on implicit differentiation. In other words, think about it. I mean, the derivative of r squared is what? 2r. Okay, but you got to think. You got to think in terms of going in the opposite. Let me move that over here a little bit. Hold on a second. So y'all can see it better. All right, what happened? Why did that 2, where'd that 2 come from? You don't know? Okay, well let's just erase it then, and we don't need it. Y'all suck. Well, think about it. You're taking 1/2, that's the r to the 1/2, and then you got to make up for that 2 in there. That 2's got to be, that 2 is a makeup. In other words, there's a makeup in there, and you got to put that in there. Why? I mean, right here, there's no 2. Happened when we were doing the, I mean, it happened between here and there. Say again? They just stuck it in there? Huh? They messed up. No. Well, we took the antiderivative right here in respect to x. The 1/2's canceled. They did what? Yes, they sure did. What did they do? Remember doing that? U substitution. Could they have done U substitution? Well, let's say U is equal to r squared minus x squared. I'm just talking out loud. Or right here. You can use U substitution here. I'm just... They did something here, and like you said, the 0 to r changed. It was negative r to r. Could they have said, okay, well, we're just going to do it from 0 to r and multiply it by 2? Could that be what they're doing? Why would they do that? Make it what? Make it easier. That's what they did. Now, wouldn't it have been beneficial to y'all to have seen that? Or had a little note out here? Yeah. So that's where the 2 comes from. Alright, now that you know where the 2 comes from, Now finish it. So y is equal to 2 over pi r squared of, well, here's our, be what, r squared, let's do this, and that'd be r squared x, right, minus x to the third over 3. Somebody check my antiderivative there. And that's going to be from 0 to what? R. Yeah. 0 to R. And now just plug R in. And then you get your direct proportion. So plug R in, and that's going to give you a 0. 0 is going to cancel that out. 0 is going to cancel here. You're going to get 0. 0 is going to go away. So y bar is going to be equal to 2 pi r squared, parentheses, r squared times what? R minus r cubed divided by 3. And then when you crank all that out, it's going to come out with some kind of related rate. Y bar is equal to 2 over pi r squared times r to the what? R to the third minus r to the third over 3, which that will give you 3r over 3, which will be 2r over 3. Lord, I hope I did the algebra right. Let's see. Let me copy this. Hold on. File, copy. Oh, if I can't do it, I got to. This thing is so screwed up. I can't copy. I have to go to File. Edit. Copy. And change screen. And now I can do paste. Sorry about that. This technology is really user-friendly. Alright, let's see if y bar is equal to 2 pi r squared times, what do we get? 2r cubed, dang old 3, and r squared will cancel with this and leave r. I got 4r over 3. Somebody help me out. 4r, oh yeah, 3 pi, sorry. 4r over 3 pi. So, first of all, remember that symmetry matters. I don't know how to spell symmetry. Is that right? Symmetry matters with center of mass. Okay? 2, get y bar, get x bar and y bar. X bar and y bar. You don't have to worry about too much about m, because m is going to be what? Masses added together, so that's not a problem. But now, what if you got something like this? And I know it's getting close to time for y'all to go, because some of y'all are having heart attacks. Let's go with something like this for y'all to work on. Find the centroid of the region bounded by 4 minus x squared and g of x is equal to x plus 2. So basically, I'm going to give you what it looks like. It's going to look something like this. That's supposed to be 4. Sorry. Can't draw. Yeah. That right there is 4. And looks like so they want to know what the center of mass of this area is. Now you can look at it and tell it's going to be somewhere, what, right here? You can look at that and tell, but you got to tell me what the actual. And you're going to have to dang old take antiderivative, dang old f of x minus what? G of x. That's the starting point. Because you got to get this region isolated. That's the first step. So then that's going to be from -2 to +1. And y'all can take off from there. Okay? Alright. Let me get the roll. And I'll put some homework up and I'll extend your other homework. So don't worry about that because I'll probably extend your other homework till this Saturday. Something like that. I got to keep y'all behind the 8 ball somehow. Right? Try to discourage you as much as possible. I'll try to fix it to where it won't cut off Saturday. You're welcome. And I appreciate the biscuit. Alright, how many people we got here today? 1, 2, 3, 4, 5, 6, 7, 8. So we're missing some people. Mr. Fowler. He relies on the videos and works out of the book. Well, he did that with Calc 1, so, and he did the work. Let's see, today's Thursday. Oh, I got to put y'all down for not here last week or last time. They'll mark y'all absent, even though class was canceled. Wasn't class canceled Tuesday? Yeah. All right, how many people we got? I said 8. All right, Fowler's not here, so I'll go ahead and mark him not here. Anybody else? Let's see, 1, 2, 3, 6, 7, 8, 9, 10. 2 guys. Okay. I know some of y'all's names, but all right, Alexander. Huh? You're sick. Yeah. Bowling. Corwin. Fowler's not here. Mealer. One of them's Mealer. Oslin's here. Robinson's here. Urban's here. Vaughn. Williams. Okay. Y'all have a good day, and I'll post the homework here in just a minute. Hopefully you'll be discouraged by the next time I see you. Oh, somebody hit my button for me.